Kuramoto oscillator network, and the theta dots are the phases. So an oscillator, just kind of goes up and down, up and down. But if I turn it sideways, I might think of it as going around a circle, right? It's going up and down, hopefully for somebody, kind of thing. So think about the angular velocities being how many cycles per second. So maybe I have a circle with a bunch of oscillators on it. Some of them are going like this, some are going like this, and then there's an interaction rule, which is given there in the equation where the sign is. The phase velocity of the ith guy on the left-hand side is a function of the sum over all the phase velocities, the j's, the theta sub j's. So they kind of talk to each other. And that parameter k is an example of the how. The where of it is on the unit circle, and the how of it, and this is a very simple example, has just got one parameter in it, and that's that k. So you might want to look at what happens to this behavior. Do I have to pay attention to the angular velocities of all 10,000 oscillators? Or maybe sometimes this collective thing happens and the situation gets much simpler. So here's my toy cartoon of 1, 2, 3, 4, 5 oscillators, and the different colors means they're going around each with their own speed. And if things happen right, I'm particularly proud of that slide. You can get them to kind of all turn. Ooh, do that again. You can get them to kind of all turn with the same velocity. So rather than having to pay attention to 5, and the 5 could be 5 million, you can just pay attention to 1. So that's an idea, an example of a emergence success story. That there was a lot of things maybe to pay attention to, but somehow when the parameters set right, everything locked and went poof, made it very, very much simpler. So here's some numerical work on that. It just kind of shows if my k, my parameter, my how parameter is too big, this guy just keeps lapping, I guess, the other guy, and they get farther and farther and farther apart. He just keeps lapping them like the Indy 500 and just keeps going around. But if the k is set lower than a critical value, the phases lock, which is kind of cool because n is n. It could be a million, and it just sort of says that these million things are going to lock into a common velocity. So that's the standard example for an emergent phenomena. Here's one occurring in nature, which I thought was just kind of cool, just to briefly bring up. It's a volcano someplace in Southeast Asia, and the water's heated on the bottom. I don't know if you can see from the top those cells that have formed, these convection cells. So here's a large number of things that don't have any intelligence to them, like crickets and fireflies do. They're somehow locked in some collective mode. So rather than have to worry about the individual velocity of 80 gazillion water molecules, I can watch the 10 or 12, and there's a simulation of how that kind of thing works, where they make a boundary by the flow going like this, and they kind of lock in with each other. So here's another example of collective emergence of some collective dynamic. So just to give you an idea of the kind of things that people are finding. So in recap, if we have an equation for a system, or maybe we have data from a system that we can sort of theorize there's an equation behind it, or we're going to make up a model equation for it, we can try to project modes and get a lower dimensional set of equations that way. Or we can hope for some sort of an emergent phenomenon to take place if we get the parameters set right. And here was another example of our emergent phenomenon. And here is my other joke slide. Tough crowd. We did the erratic croissant, our example of an attractor of one of these 1.2 dimensional manifold kind of thing. So that's basically the lay of the land. We have chaos and emergence in complex systems kind of represented on that slide. And they're all examples of dimensional reduction. Right? That's what we wanted to do. We wanted to look at internet traffic and understand at a glance somehow what it was doing, and be able to, as humans, be aware of, the comings and goings of that. So here's my other jingle slide. On a good day, if we do it right, yes, we can get low dimensional answers to high dimensional questions. So that sounds really, really hopeful, So that's why people around DoD are funding things like research and, the internet as a high dimensional dynamical system, or the notion of emergence, and also the Therminator work. The benefit being the dimensional reduction. Okay. So what does this say? Right. Okay. So if we win, we get these low number of modes. Say 5, 6, 7, 8, 9, 10 modes. So here's an example of what familiar modes are. So the sounds of an orchestra. So I can tell the tubas from the percussion. I might not know what color tie the guy with the cymbals is wearing, but I can course in the orchestra, and I can kind of break it down into a handful of sounds, And the smells of a pizza parlor is the same. I can smell mushrooms and I can smell onion. I don't know if it's a red onion maybe or a yellow onion, but I can just kind of group these smells coming out of a pizza restaurant into modes, this kind of a thing. Okay, and the modes may interact. That's kind of a joke slide, but maybe that's not that funny either. Thank you, God. Thank you. People work hard on these jokes, really. Okay, so there you go. Right. So how did they interact with these various mechanisms? Through an equation, through their action on various, polynomials. Mechanically, chemically, if it's a physical, chemical experiment type of thing. Logically, if it's a circuit. So there's ways these modes interact with each other. Okay. And the modes are system specific. So if we break down the, I guess it's the complexity on the top arrow and the chaos and dynamical system stuff on the bottom arrow, if we want to get the modes, we take the interaction rules and the graph construction, and so we had that parameter k. If it was too high, I think the phases diverged. If it was low enough, they phase locked. There might be 10 or 12 such parameters in a more realistic kind of a high-dimensional thing of interest. So you kind of have to exhaust the phase space and just kind of poke around and say, anything emerge here? Well, no. How about over? That can take a long time to, a 12 by 12-dimensional cube and exhausting the space, that can get pretty computationally intensive. So people come up with these genetic algorithms to kind of optimize search, and it's a whole subject into itself. But basically, you kind of got to poke around and guess, which is kind of basically what that says. And in the case of the dynamical systems, the Foyas guy, who was our light in the darkness, who said, yes, if the PDEs have this squeezing cone property, you can go from this high-dimensional, even infinite-dimensional system to a low-dimensional one. Someone asked him, well, how would you go about finding these low number of modes? And he said, I would ask, basically, his sentiment, my words, he said I would ask a subject matter expert. So, if, for example, if I was dealing with a fluid, I would go find an experimentalist who knows a lot about fluids and ask him what did he expect to see. Because people, what modes do they see when they go to actually implement this kind of thing? And I would ask. So that's why I say make a best guess kind of thing. So Foyas says ask, and say is something you can do if you can project, but we don't have to talk about that today. So here's the cybernetics slide. A guy named Norbert Wiener, famous guy, 20s, 30s, 40s, and 50s, MIT guy, contributed to a lot of different places. Cybernetics, there towards the end, which kind of has a bad rap because it kind of got absorbed into, popularized in places, maybe the softer sciences, so maybe it has a thought of maybe as more of a wishy-washy kind of circle of ideas than maybe that it really is. But something that I think is relevant for what we're talking about right now is he says something about the behavior of such systems may be interpreted as directed to the attainment of a goal. So when people are saying, how am I going to find these modes? I've just constructed this big complex machine with a lot of moving parts in it. How do I know what the modes are? Maybe these modes were designed to do something, and maybe they're just simply trying to do that. So it's kind of a pointer on what path to take. So the next part of the talk is be careful you get what you wish for, because what if we get these low-dimensional modes? What are we going to do with them? Okay, so I called it post-traumatic distress disorder because we went through all this work to maybe get these modes, and now that we got what we wanted, we don't know what to do. You almost laughed. I saw it. That was good. That was thank you. Okay. I try to put a joke on like every other slide, so just laugh on the odd ones and probably okay. Huh? Oh, okay. Well, you're exempt. You're having fun with your voice today. Yeah. Okay. All right. So suppose that I got these modes. Now what am I going to do? So how do I make good use of that? What business am I in now? So the thing is, I think it's thermodynamics, and I'll try to tell you why I think that. So then this is nothing that I've come up with. This is just the standard stuff. And of course, remember, this is a very old discipline. It's like 1820s, or if you think about people trying to measure temperature of vats of bubbling stuff in the Middle Ages, it's even older than that. But sciencey